I said that you can't really, that radicals are not very stable, and you can't really put them anywhere. You can't put them in a bottle. Anybody know an exception to that? You're swimming in it.
Chlorine.
You're swimming in chlorine?
Right? In like a pool?
Oh, okay, okay. Sorry. No, that makes a lot of sense. I'm really sorry. That makes good sense. But chlorine gas, you would not. I need to look up how toxic chlorine gas is. It's chlorine gas is really toxic, and the amount. Have any of you maintained a pool? Like chlorinated a pool? I haven't done it in 30 years, but it's a tiny amount of stuff to put in there. It's actually bleach, more better way to put it. O2 is a radical. So O2 has this Lewis structure. And like I said, I need to shut up on this. This is not what we're doing next, but I could talk about this forever. All right, so O2 is not O double bond O, the way you would like to draw it. It's O single bond O. Each of the oxygens has an unpaired electron. So each of the oxygens is a radical. And those, when I say unpaired, I've shown them both up, spin up, plus half say. When you say unpaired, what you mean is they're not paired. So if I know one of the electrons is plus half, I have no idea about the other. If the spins were paired, and I said one of them is plus half, I'd know the other one was minus half. All right, so unpaired, they could both be up, they could both be down, one could be up, one could be down. Anyway, that's oxygen. It's actually super reactive. Right, the atmosphere is about 20% O2, which is, I hope, like I said, some of you are going to be bio majors, so you probably know that you have to have O2 to live. Hopefully everybody knows that, right? O2 is toxic. Anybody scuba dive? Cool. If you go below, it's like 20 feet, right? Breathe in pure O2. You should know this if you scuba dive. You stroke out. Okay, so you can't actually breathe oxygen with a partial pressure more than 1.6 atmospheres. Your brain can't deal with it. Nobody really knows why. So O2, you have to have it to live. It'll kill you. And it actually will kill you, right? We get fires that way. Stuff you leave out will just rust. Like O2 is super reactive, and it's the unpaired electrons that make it that reactive. Man, that would be a fun class to teach. Instead, let's go to chapter 9. Alkynes, carbon-carbon triple bonds. How many carbons are in that molecule that I just drew? Remember that. Those are some very confident fours. 1, 2, 3, 4. The triple bond bonds two carbons together. And I notice new chemistry students often see that as like two carbons that are triple bonded together. So, and I think it's something that happens in speed, that you don't actually see this as a junction, right? And it's linear. The hybridization of the alkyne carbons is sp. Those carbons are linear. Okay, so this is the proper way to draw it. You will sometimes see this drawn with a bend. Do that for Dr. King next week. She's having too easy a semester. She needs to see that. This is going to be the same thing as like drawing wedges and dashes on alkenes, right? I'm going to take off for it, but I get it. You just need to, you want to always draw your molecules with the proper geometry, or as close to it as you can manage and make everything clear, right? So sp carbons are going to be linear. So make sure you draw this alkyne linear. If you draw that bent one, I'll probably at this point, since it's a week away from the exam, I'll probably just note it. But you really should change that. All right. So here's the thing. Let's do this. So if we take that alkene and add HBr, we're going to add H and Br across the carbon-carbon pi bond. If we add an equivalent of HBr, so a mole of HBr per mole of butane, we'll get both of the, we're going to add HBr across that carbon-carbon triple bond. We're going to have one of the pi pairs react with the HBr. If we add more HBr, we'll add another equivalent of HBr. But you can stop here. Right, that Br, remember, it's electronegative, so it's actually making that alkene a little less nucleophilic. The Br has a lone pair on it, but its electronegativity dominates, and it makes the pi electrons in that alkene in the middle. This alkene is less nucleophilic than the alkyne pi electrons, right? So you can, if you treat with one equivalent of HBr, you can stop here. You're going to get a mixture of diastereomers. More HBr goes to the dibromide. Point being there, the alkynes are going to do pretty much the same chemistry as the alkenes. Like a lot of the reactions are going to be just like the alkene reactions, with some twists, right? So if one pi bond reacts, you're still going to have another pi bond there. So the simplest thing to have happen is just what you see going all the way to the right. The alkene, the second pi bond does the same reaction. There's going to be a few modifications of that, and we'll start looking at those. We'll pretty much do all those on Tuesday. There's really one reaction in Chapter 9 that is completely unrelated to the chemistry you see in Chapter 8, and that's what I wanted to focus on today. It's not this reaction. So probably you're going to be looking at Chapter 9. Almost all of those reactions at least start the same. Pi electrons attack something, and then you get a product. How's that for? It's a quality teaching right there. Mix reagents together, something happens, you get a product. Man, that's Orgo 1 and 2, and advanced organic. You can just go home now. All right. You might remember back to ARIO from Chapter 3. That O out there is orbital. So having a negative charge, having an anion lone pair in an sp orbital is more stable than having it in an sp2, is more stable than having it in an sp3 is what that O means. And so if you look at this orbital, a proton bonded to an sp carbon has a pKa of about 25. That is not very acidic, right? pKa of water is 15. So a terminal alkyne proton has a pKa, a terminal alkyne proton is, like 1 trillion times less acidic than water. But if you compare it, it's about the same magnitude jump to ethylene. The proton on ethylene has a pKa of about 40. That's way less acidic. And then finally, the proton on ethane has a pKa of about 50. And I've said this before, you really can't make the conjugate base of ethane by pulling a proton off. There's no acid-base reaction we can do to just take that proton off. You have to make that conjugate base a different way, and you'll see that. It sounds like I say this a lot now. You'll see that in Orgo 2. The only one of these you can actually do a reaction, an acid-base reaction with, is the alkyne. And so if you treat this with a strong enough base, the one the book uses the most is NH2 minus, amide. You get just a proton transfer. The NH2 grabs this proton, the lone pair goes onto that carbon, and our product is that. Again, this is 2 carbons here. So there's an sp carbon here bonded to a methyl and triple bonded to a carbon. This carbon, the terminal sp carbon, has a lone pair and a formal negative charge. Okay? pKa of, and you get ammonia, pKa of this one is about 38. So again, this reaction favors the products by about 13 orders of magnitude. The other ones you can use, there's quite a few, well, I say quite a few. They all wind up boiling down to like a localized N minus or a localized C minus. So diisopropylamide, N minus, N minus. And the other one you can use here is a molecule called butyl lithium. Right, that lithium is going to be a plus. It's going to react like it's a plus. The carbon like a minus. That's basically, that's the conjugate acid of this anion has a pK of about 50. So you need a super strong base to do this reaction, but we have super strong bases. And so if you treat a terminal alkyne is going to have an H on one of the 2 carbons. At least one of the 2 carbons. Treat a terminal alkyne with a really strong base, pull the proton off, you get the conjugate base of the alkyne, which is this anion. And now this anion, right, it's kind of bullet shaped, looks a lot like nitrile. This is a pretty good nucleophile. It's a strong base and a good nucleophile. So, draw the product of that reaction. let's look at the one on the left. So, I know I had just put this up. All right, so you gotta see, if there's no carbon on that alkyne at the end, there's an H there. The N minus will take the H. We'll get a carbanion. That's your carbanion. And now, if you look at your, I think it was, no, maybe it was the other exam. Look at some of these. Can't remember the questions. Yeah, never mind. So in benzyl bromide, let's go through the chapter 7 steps. Is there a leaving group in benzyl bromide?
Mm-hmm.
There is. You could have had your eyes closed for that, right? I said bromide. Are there beta hydrogens? No. So this is the one I did. So you remember, all of you that have your exams now, the question where I said, hey, I just gave you some points. There's hydroxide and carboxylic acid, and you're just going to take the proton off. And, like, the average was not good on that. The same question I thought I was doing to the other section was benzyl bromide with potassium methoxide at 100 degrees. Right? There's no beta hydrogen. The only reaction it can do is substitution. You cannot eliminate if there are not any beta hydrogens. But I said 100 degrees, so everybody got in their formula right. Good leaving group, strong base, 100 degrees, it's an E2. It's not an E2 if there's no beta hydrogen. So here, even though you've got a really strong base, good nucleophile, if there's not a beta hydrogen, all it can do is SN2. So I didn't put temperature here, but you don't need to know the temperature, right? Substitution reactions can happen at any temperature. It's not like a substitution reaction can't happen at a high temperature, it's just that elimination reactions happen faster in our favor. Yeah?
We should not get to the tertiary carbon since it's the carbons.
That carbon?
Yeah.
How many carbons is that bonded to?
But it's double bonded to the carbon.
No, that carbon is single bonded to that carbon. Right, so the reaction, maybe I should, I'm not kidding around, like I often write small if you're in the back row. So, this is the carbon that's going to react. It's got one bond to it, 2 H's, one bond. It's benzyl, and a phenyl group is actually really small. It looks the same, I erased the way they get drawn on the board, benzenes and cyclohexanes look the same, just with 3 double bonds. But the carbon-carbon double bonds in the benzene ring, right, that actually all the carbons are kind of a bond and a half. This is planar, so the cyclohexane is this chair, stuff sticking off. You remember all this, right? That thing's huge. This one, there's the side view. All right, that's benzene in a side view. I'm exaggerating in these drawings, all right? And I'm picking on your question. Benzene is a lot smaller than a cyclohexane. The way we represent the molecules on the board or on paper make them seem like they're kind of in the same ballpark. They're really not. A cyclohexane is enormous compared to a benzene ring. And so your question about, is it sterically hindered? No, it really isn't. And based on the phenyl ring, this gets into hyperconjugation. The benzene actually helps that substitution. So benzyl bromide does this into really well. And one of the reasons is it can't do E2. So you can heat this up, right? All reactions go faster at higher temperatures. They just might not, other reactions may rise, the rate of other reactions may rise faster, and the equilibrium constant may get knocked down. But this reaction, you can heat this reaction up, it goes really well. So the product here is this. You got to keep track of how many carbons you have in there. Okay, so you're going to end up with 3 between the benzene rings. 1, 2, 3. And now, if you haven't already, you're going to go into Wiley Plus and the book, and you're going to look at all the reactions that alkynes do. You can add water to them, you can ozonize them, you can add HBr, you can do hydroboration. All the stuff you can do in chapter 8, you can do in chapter 9. So let's come over here. Take a look at this reaction. And now there is a difference. You're not going to get the same reaction over here. That's what I'm going to tell you. All right, so now same thing. We're going to make alkynide anion, pull a proton off that terminal alkyne CH. But now, okay, isopropyl bromide, leaving group, beta hydrogens. Now, is it sterically hindered? Secondary. All right. 1, 2. The secondary, so if it's tertiary, it's easy. Right? If it's tertiary, you can't do SN2. It's going to be E2. Turns out this is a strong enough base, this is still going to be an E2. You're going to wind up with and sodium bromide in ammonia. It's a very expensive way to not do anything to that starting phenylacetylene. So it's an E2 reaction. Right? Now the book will say here's what the book says. It's definitely right about that last statement. All right? So if you take the acetylene anion, sorry, not the acetylene, the alkyne anion, and you try to attack a secondary or a tertiary halide, it's not going to do substitution, it's going to do elimination. The book says primary halides work to do substitution. And what I will tell you is, yeah, that's probably true. And we're going to use that. You'll use that in a lot of book problems, a lot of Wiley Plus problems. But these have to be done at low temperatures. And honestly, the several times I've tried to do this, I've gotten a ton of E2 reaction with it. So you get enough that you can pull out your product, but you're not going to get anything like a high yield. It's a really good reaction with things like benzyl bromide, benzyl chloride, where there are no beta hydrogens, methyl iodide, again, no beta hydrogens. Right? You can put a methyl on there all day long because you literally cannot do an elimination. With anything that can do an elimination, you got to be really careful. For the purposes of this class, you can do what Professor Klein says. Do SN2 if you need to make a molecule. Questions there? All right, let me put up one last thing for the day.
You have 2 minutes left.
I can do this in 2 minutes. Of course, the question is, can you do it in 2 minutes? What is the product of that reaction? Next show, guys. Cliffhanger. It's the key to